Okay, let's go. I'm Alina. I work as a developer advocate for GraalVM at Oracle Labs. And Oracle Labs is this very cool R&D unit at Oracle. We are doing a lot of research. So many of our project has been research projects for many years, like GraalVM. And we do research in areas like programming languages, compilers, VMs, all kinds of things. And in this session, I want to talk about Java applications in the cloud and how you can make them more efficient with GraalVM. Let's go. So first thing, I want to give you a brief overview of what GraalVM is, because it's a huge project and there is so much in it that sometimes it gets confusing to figure out when you should use it and for what. So one thing is that GraalVM is a JDK implementation on its own. Underneath, it's using the hotspot VM, the same kind that you will find, for example, in OpenJDK, and we are just replacing the top-tier compiler. So as OpenJDK has C2 as a top-tier optimizing compiler, we have our own GraalVM compiler that is coming out of this research that we've done at Oracle Labs. And in this scenario, if you want to migrate to GraalVM, migration is very easy because it's a JDK. So all of your libraries and tools and IDs and everything just works. And what you can get in this mode is more performance potentially coming from this new compiler. So that is one big part of the project. And another big part is this native image ahead of time compilation of Java. That will be something I will talk about today in this session specifically. And that is when we take a Java application and fully compile it ahead of time into a native executable that can start and run time very fast because it no longer requires a JVM to run. So it's a fully natively compiled native executable. And last but not least, GraalVM is also a polyglot VM. So we have a language implementation framework called Truffle that allows us more easily implement more languages on the JVM in a way that we as a team, or for example, you as a community member, can just write your interpreter for your own language in Java and run it on GraalVM, and then at runtime it will optimize it and give it high performance. But that's the way we as a team and our community implement more languages on GraalVM. And at the moment you can use languages such as JavaScript, Python, Ruby, R, etc. on GraalVM as well. And not only you can use one of those languages, but you can also extend your application with other languages. So it can also run programs that are using more than one language at the same time. So that's an overview, and now let's focus on Java. So what is interesting in GraalVM specifically for Java is the following. One thing, as I mentioned, it's a full-blown JDK, so you can just run your applications on GraalVM as you would on any other JDK. But more interesting part is this native ahead-of-time compilation of Java programs, because since we are optimizing and compiling your application at build time rather than at runtime, they are way faster and consume way fewer resources because there is no code to optimize and compile at runtime. And because of that, this native image ahead-of-time compilation is a great deployment platform specifically for the cloud, because in the cloud you want to start fast so you can deploy faster and scale faster, but also you want to use less resources and specifically less memory, because that's a big part of your cloud build. So if you can deploy the same application using less memory, that will be much more preferred way to deploy them to the cloud. And because of all those reasons, all the major Java microservice frameworks already adopted GraalVM and native image specifically as a deployment platform. So if you are starting a new app and you are using any of those frameworks, they will give you tools and ways to start out of the box and fairly easy write your application for GraalVM. Okay, so let's talk about some specific things you need to know about GraalVM to start building your applications this way, and also what are the benefits that GraalVM gives you comparing to deploying your application on a JVM. So one thing you want to have is start your application fast, because that's a bad experience for your users, but also, again, it allows you to deploy and scale your applications faster if the same app can start significantly faster. Now also, if you can reduce resources usage, and we are talking about CPU and memory here, that will be also preferable because you would be using less resources at runtime. And another interesting aspect, and this is not cloud specific, but applies to the cloud as well, native image as a deployment model also offers some additional benefits around security, and we will take a look at it in a bit more along the presentation. And the last thing is that it also gives you a way to package your application in a very small, efficient container images. So again, so that you can deploy them faster and scale faster as well. So let's talk about each of those aspects, and let's first talk about how it's impossible to take something so dynamic and sophisticated as a Java application and fully compile it ahead of time so that it can be available at runtime. So the way GraalVM and Native Image does this compilation is the following. When you run the native image command and give it your application, and as an input it takes your application in bytecode form, what it will do, it will look at your application at runtime, and it will starting from the main entry point, it will look for all the reachable code. So it will try to find all the code that is actually needed for your application to perform at runtime, whatever is the work it is supposed to perform, and find only that reachable code and then eliminate everything else. So everything else that your application is not using will be eliminated, and this applies to the code that you actually wrote, but also to the dependencies, even the JDK classes. So in this final produce native executable, only the code that is actually needed at runtime, only that code will be included. And that's the ahead of time compilation part of the story, but there is another big part of this native image compilation, and that is heap snapshotting. So one more thing we will do during this build process is we will take a snapshot of your heap so that you can start with pre-populated heap at runtime faster, because all this work doesn't have to be done at runtime anymore. And that is the main idea behind native image. So we are kind of splitting the work that you are doing to deliver your application into build time and runtime more explicitly. And the idea here is to move all those expensive, heavy lifting operations from runtime to build time, so that you can do them once at build time and don't need to pay this kind of overhead work when you actually run your application, because most applications are started way more often than they are built. So it makes sense to build the application once, spend time and those computational efforts at build time, so that you can start much faster when you actually need to run your app. And if you're comparing running on a JVM versus running in this native image ahead of time compilation mode, the comparison in terms of startup times will be the following. So when you're first starting your application on a JVM, what needs to happen is the following. The JVM needs to load your classes, look at them, figure out what your application does, start interpreting, start collecting profile information. And what happens at this period of time is that some methods will be compiled dynamically at runtime, but some methods that are not executed that often, so they are below this threshold, might still be executed in interpreter, and interpreted is much, much slower than compiled. And maybe it wouldn't have a big runtime impact because those methods are executed less often, but if there are many of them, this can add up and have a runtime impact in terms of performance. But this is all happening dynamically via interpreting, collecting profile information, compiling, and then at some point when your application warms up and all of this work is done, it can finally run with the best optimized peak performance. And this is the reason why sometimes, especially if you have a larger application, you can notice that those cold startup times when you start your application for the very first time can take significant time. Now, if you're compiling and executing on the native image, so in the ahead of time compiled mode, what needs to happen in terms of startup time, since we already analyzed, optimized, and compiled the application at build time, what happens at runtime is the following. You need to load the executable, and since all that code is already compiled, it can immediately start executing in this natively compiled mode with good peak performance. So this is startup time, but let's also talk about resources usage. So similarly to the way we spend some time in this JIT mode to start your application, the same applies also to resources usage. Because we span all those operations, we also need memory for all of them. And we need to keep around memory for your application itself, but also for all this kind of code execution infrastructure that is executing your code dynamically at runtime. While on the native image mode, so ahead of time compiled application, you need memory only for these slim runtime implementation that native executables contain within themselves at your application payload, but you don't need to keep around memory for all that code execution infrastructure because there is no dynamic code compilation happening at runtime. And this becomes even more meaningful if you want to scale your application. So as you scale, you would need to add memory for all those things if you are scaling on JVM by adding more instances, while in the native image mode, when you're scaling, you only need to add more memory for the actual application payload. And to illustrate this a bit further on the more kind of real-world example, here we are scaling a Quarkus application. the yellow bars that is running on a OpenJDK, and the red ones that is in this native image mode. And as we are scaling, you can see that we, on the JVM, as we are adding more instances, we need to add significantly more memory because each of them will need to use all this memory to actually run and execute your code. While in the native image mode, you see that memory grows a bit over time, but it's uncomparable because it's way more efficient at utilizing your memory. Okay, I think that's enough of talking. Let's look at some demos. And first, we will talk about startup and memory usage. So let me just get to the right place here. Okay, so this is the first demo I want to show you, and here is my app. Let me just move this down. So as you can see, this is a Micronaut app in this demo, but could be any of the frameworks I mentioned above, or even just a sample vanilla Java application. So this is my application, and here's my controller, and what it does, it exposes this endpoint hello, and I will now run a bunch of tests against this app to show you how it works on both the JVM and in the native image mode. So let's do this, and let me clear this. So let's run on the JVM first. Okay, this runs, and you can see here that the startup times that the framework reported to me, so this is coming from the framework, startup time here is 500 milliseconds. And then if we go to the browser and we check on our app, and the endpoint is hello, here is our message. So let's kill this, and let's compare this with the native image mode. And let me just confirm that this is indeed now down. So this is not loading anymore. And let me go ahead and let me run this in the native image mode. And let me also show you how this what this native executable looks like. So it's here in target, and this is my app. It's called Simple Rest here, and the size, it's not that small. It's 81 megabytes, but it's my app fully ready to go with all the dependencies and everything included in it. And also, if I wanted to optimize the file size itself, there are some optimizations that I could apply. So I could use something like UPX, and since this is a native executable, I could compress it even further. But here, I'm not concerned about the application size, so for me, this is sufficient. So let's run this native app. And now it started in 22 milliseconds, so I would say this is roughly 25x faster. And if I go to the browser and update this, so it's doing the same thing. So it's the same app, it's just being executed in those two different modes. But those are the numbers that are coming from the framework, and maybe I want to, and also there could be different opinions on what is startup and how it should be measured. So maybe I want to measure it myself from the kind of operating system kind of level, and also in a framework neutral kind of way. I just want to have my own numbers so that I can believe them. And also maybe I want to measure not just starting the app because it's not very meaningful to me. Maybe I want to measure how long it takes to start the app and serve the first request, so do some meaningful job. And for that, I will do the following. Here I have my start script that will start my app, and it will wait for the first request, and then it will print those performance numbers for me. So let's do this. And another thing that I will do there is I will use this switch between the scripts, so I can just switch easily between the JVM and native image modes. So let's go to our app, and let me start it again on the JVM. So it started, and it also printed out those performance numbers for me, and I'm interested in startup, and the actual time elapsed here, again, this is on a JVM, is 1.17 milliseconds. So let's do the same experiment in the native image mode. So start the app and measure how long it took to start. So it was 1.17 before, and now it's 0.08. So again, if we are even looking from the outside, trying to be as objective as possible, it is still much faster. But this is just startup, and maybe I have a longer running application, so maybe I care about startup less, but maybe I do care about those resources that my application is using at runtime. So for that, let's look at our app again. And what we will do is the following. We will start our app and we will send a couple of requests over time. And we will also use the tool called PS Record to look at my process and output this information about CPU and memory usage of my application. So let's do this. And let's do this on the JVM again first. So this is starting, and now it's sending a couple more requests so we can look at our application and how it behaves over time. Okay, now it's done, and I just have this new file created over here, and this is my application over time. So let me zoom this in and let me show what's happening here. So the blue horizontal line on this chart, that is memory usage by my process. And you can see that it's, I would say, about 200 megabytes, but it was a bit more in the beginning. And the red vertical line, that is CPU usage. And what's interesting here is what is happening until the first, I would say, 1 second. You can see that both CPU utilization is quite high and memory usage is quite high. And that is because we are starting our app on the JVM, and there is this cold start kind of period where it's doing a lot of work that we've seen before around loading our classes, interpreting, compiling, profiling, etc. So it's quite busy, but then it evens out over time, but in the beginning it's quite busy. So let's see the same, but for native. So the same, now we are sending some load, and in the end we will get a similar chart that we will compare with this one. Okay, it's done. And this is my second chart. So as you can see, this is looking quite different. A few things to notice here is that the overall memory usage is lower here, around 100 megabytes. But also CPU is not so busy in the beginning anymore because there isn't that much work to do in the beginning. And it's only busy once in a while when those requests arrive and need to be served. But then when there is no work to do, this application is quite efficient because when being idle, it's not using resources when there are no requests to be served. But we all know and love JVM for peak performance and how it optimizes our application for the best possible peak performance, having that profile information available and adapting on the go to what our application does. So what about peak performance? Let's look at that as well. So let me clear this and let me send some load to my app, and I will show you what it does in a second. So what happens here is, where is my load script? What happens here, I will use a tool called Hey to send 1 million requests to my application to see how well it handles peak load. And it printed out this nice, quite extensive performance report for me. We could be looking at latency, but for me, always the most interesting thing to look at is peak throughput numbers. So here, what I'm getting in terms of peak throughput is 108,000 requests per second. So now let's run the same in the native image mode, and let's see how our native application can take the same load, so 1 million requests. Who thinks this will be slower? Okay, who thinks this will be faster? So typically people say that, ahead of time compilation, there is no way on earth it can be faster than dynamic compilation at runtime, but let's compare. So what happened here, we have 109,000 requests per second, so slightly faster, but I would say in general on par. And I'm gonna say that this is with all the possible probably optimizations. But the point I wanted to make here is that it's possible to, in addition to startup, resources usage, etc., it's also possible to have an on-par great peak performance in the native image mode as you would normally have on the JVM. So that's one conclusion I wanted to make here, but also what about resources usage? And maybe the app that I'm working on doesn't need to serve huge peak load, or maybe it's even my pet project, some hobby project that I'm doing on my weekends, and I want to deploy it on a machine that is as cheap as possible and make it use as little resources as possible. So maybe over peak performance, what I want to prioritize is low resources usage, and I don't care about that much about peak performance. So for that, I will run this app again, and I will do the following. So that will be my native constraint profile. This looks good. And now what it does, it will run the same application, only this time with 32 megabytes of memory. And previously, we were giving the app in both native and JVM modes. Let me move this down. Previously, we were giving 256 megabytes, so now this is 8x less memory. Okay, so seems like this is complete. We got all our responses. They were all successful. And if we look at peak throughput, it got a little bit lower. But if I want to prioritize resources usage, I think this is good enough. So the point that I'm making here is that as many things in life and in software engineering, this is a bit of a trade-off. So maybe I want to optimize for peak throughput, and I have a way to do that. But also maybe I want to optimize for resources usage and reducing that. And there is also a way to go for me because, again, we don't need that many resources at runtime because everything is compiled ahead of time at build time. So you can choose depending on what your priorities are and what you want to accomplish for your app and your project. Okay, and let's talk about one more topic, and this is the part that I like a lot about Native Image because it's quite famous for startup times and memory usage, but there is another interesting aspect to it, and that is security. So Native Image as a deployment model offers you some additional security benefits, and they're coming from the following. One, since there is no dynamic code execution at runtime, there is no new unknown code that can be loaded at runtime. So everything needs to be known in advance at build time because the way we compile those applications ahead of time is under a closed world assumption. So everything there is to know about the application needs to be known at build time, and no new code can be loaded anymore when you actually run your application. And this can be seen as a limitation because, again, you need to figure out everything your application does and provide this information to Native Image when you actually build your application. But I think it also can be seen as a security benefit because nothing unseen can be happening at runtime. Now, also, only the code that is reachable, so that Native Image saw and kind of confirmed that it's reachable from the main entry point, only that code can be included in your application. So if you are using a lot of dependencies and maybe you're not so sure about some of them, the parts of those dependencies that you are not actually using will not be included in this final produced native executable. And some things, such as, for example, reflection, serialization, those more dynamic Java features, those can be configured to work with Native Image, but they require an explicit allow list from your side because, again, closed world assumption, so all those things need to be configured and provided to Native Image at build time, and you have more control over those features. And also, this is an additional security level because you are telling specifically what to use and how to the Native Image as you are building your application. And last but not least, some attack vectors, and especially those around just-in-time code compilation, are just impossible in Native Image because there is no just-in-time code compilation anymore. It's all compiled ahead of time at build time. So there is no just-in-time code compilation, and all those attack vectors are simply impossible with Native Image. And for that, let me show you another demo. And this one is called Very Suitably Unsafe Demo. So don't repeat this at home. Okay, here it is. And I want to apologize for my voice. I think I'm getting sore throat, but I think we'll manage to the end of the presentation. So here is my unsafe demo. And this is, again, a micronode application that will be serving a web server for us. And what we want to do here is we want to serve the static content from this static folder. And basically, we want to serve this hello HTML file. So let's run this app. Again, we will start with the JIT mode. So it's starting and it's running on 8080. So let's go ahead and see if we can access our file. So this is on static and the file is hello HTML. Okay, so this seems to be working. But let's imagine maybe somebody else, a new developer, joins our team and they decide to implement this logic in the following way. So instead of serving this static content dynamically, statically from the static folder, they want to implement this as a get endpoint and then retrieve the file by the name. Does anyone see any problem with this code over here? Those of you who know, please don't say it. Okay, but maybe other people see some issues with this as well. Okay, let us see how this works. So now it's the get endpoint, and it adds this static URL part to it, and we are retrieving our file by name. So let's see how this works. The endpoint is get, and then we need to pass the file name. So this seems to be working. It's all fine. And let me switch to curl so I can make this a bit more visible, hopefully. So now when we curl this endpoint, it also seems to be working file, right? We are getting our hello HTML file. This is all great. And of course, we want to test that our implementation works correctly. And let's curl some nonsense. OK, this doesn't give us anything amazing. Let's ship this code. But this also offers some additional interesting opportunities. So imagine I'm doing the following. So here I can do, let's say, let's go one level up. And let's do application YAML. Okay, do I have my double quotes? Yes. Suddenly, my application YAML file is exposed. Of course, this is not very production-grade kind of code, and maybe I should have, and probably I should have user input sanitized and had some additional checks in place. But you know, we all know that it might be easy to make a mistake like that. So suddenly, my application YAML file is exposed. And it doesn't stop there. So what I can do, if I try it hard enough, or maybe spend some time here, I could also do example. What is the package name? Micronaut. And let's imagine I know this will be a hello controller.class. And I'm not going to print it out here, but this would have given me the class file itself as well. Luckily, we also have this app compiled to native. So it's over here again in target. This is my natively compiled version of it. And let's see how that app behaves. So target Micronaut guide. It's started. It's on. Let's go here, see if we can get our hello HTML. OK, it's all there. And if we get it from our get endpoint, it's also there. So let's see if we can expose those vulnerabilities about our app. So let's go back here. And if we try to get this application YAML file, it doesn't give us anything. And if we try to get this hello controller class out of it, again, it doesn't give us anything because there is no longer application YAML and controller class. It's all now natively compiled. And those people trying to access resources of our app will have much harder time, if possible at all, trying to get those resources because it's all natively compiled and everything that is not there is eliminated now. So this is an interesting additional security level that Native Image gives you as a deployment platform comparing to executed on the JVM. And just one quick example of how this is being used by some companies and teams. This is actually coming from Oracle itself. So we have our fellow team at Oracle Customer Experience Industry Framework, and they said that yes, we are using Native Image because we like startup time, we like how small our container images got, but also they said that they appreciate the security angle because they care about security a lot, and they can see how this native ahead of time compilation is beneficial for their security as well. And let's talk also about compact packaging. So what Native Image produces, as we saw in the demos as well, what we get in the end is this final compiled native executable version of our application, and that also includes all the JVM runtime and JDK classes code that we might need for our application as well. And all the unreachable codes, so all the things that were not proven to be actually used in your application, all of that will be eliminated. And in a way, again, this can be seen as a disadvantage because with normal Java deployments, you could share this runtime installation. But again, this also means that maybe if you need to patch and update those applications, then can be patched and updated individually as a native executables as well. And if you're talking about building containerized applications specifically for the cloud, here is how low you can go with your application container size, and the red bars here, this is running still on the JVM, and then the green ones that is running on GraalVM Native Image, and we are trying to make it as small as possible and squeeze it to the bare minimum. And you can see how in the end we get to something like 6 megabytes of our image size. That is a fully working, fully functional, minimal, but still Java application. And that is natively compiled ahead of time, fully static, but also compressed to make the image size as small as possible. So if you want to optimize for this packaging size, that native image probably is the way to go for you. Okay, so what's the catch? I don't want this session to sound like a sales pitch and just talk about benefits, so I want to talk with you a bit about limitations or other things to be aware of as well. So one thing is GraalVM and reflection. Did anyone here hear that GraalVM doesn't support reflection? Quite a few people still we have a way to go to destroy all those myths. So GraalVM does support reflection, but the way it supports reflection is the following. So as we said, native image compiles the application ahead of time under closed world assumption. So all those dynamic features of Java pose a bit of a challenge because runtime hasn't happened yet. So there is no way for native image to know in advance what will happen at runtime and configure those dynamic features. But there are ways to approach this. So one thing is that some of more kind of predictable obvious reflection calls, native image will figure out of the box without configuration because it has support for all those basic kind of predictable reflection calls. Now, for things that are a bit more advanced and a bit harder for native image to figure out automatically, you would need to provide configuration, and that comes in the form of JSON files. So those will be needed for things like reflection, serialization, etc., if that configuration is not coming from your library, framework, etc. So you might need to provide this configuration yourself. But again, there are good news for this. So native image, when you get your GraalVM distribution, comes with a tracing agent, and you can run this tracing agent and run your application on the JVM. And what this tracing agent will do, it will observe your application behavior, and it will produce this configuration automatically, again, in the form of those JSON files. And this is very helpful. I will not say that this is a silver bullet. So we do recommend that you still go through that configuration and make sure that it's complete and kind of critically review it. But it's very helpful to eliminate a lot of that manual work and make more of those dynamic features in your application work in the native image mode as well. And then what about reflection in those third-party libraries? So maybe you know what your application does and where and how you're using reflection, but it might be way more challenging to configure reflection for some third-party dependencies that maybe you don't know that well. So in that case, the preferred scenario is that this library or framework ships configuration for native image itself. And indeed, we see quite a few libraries in the Java ecosystem already adopting GraalVM Native Image as a deployment platform and shipping this configuration within the library itself. So if you check out, for example, the source code of the H2 library, it already contains this reflect config JSON file that will tell native image where and how H2 is using reflection. So it's possible to build application using H2, and that also does reflection at build time. But for those libraries and tools and frameworks that haven't adopted native image yet and don't ship this configuration yet, we created this centralized repo on GitHub where those library users and framework authors and just other native image users can contribute, share, and that reuse configuration for native image, because it could be the case that somebody else already solved this issue with a particular library that you are trying to use. And it's very helpful having that centralized place where you can pull this configuration from. And what's even better, we have native build tools, that is Maven and Gradle plugins for building projects with GraalVM Native Image. And there you can enable as a parameter in your build file access to this repo. So if you are using some libraries and tools, this will give your plugins access to the repo, and they will go and try to configure and pull this configuration automatically from this place, so you don't even need to know about configuring those external dependencies. Okay, so talking about things to be aware of and just limitation that you maybe want to know about working with native image. So indeed, there is a required build time step. So build time step becomes more important because a lot of work is happening during the build time. And also, what is important is that there is like significant computational effort needed at build time, because Java applications are complex and dynamic, and it means that to compile them ahead of time and to analyze the whole application, then optimize and compile it, it might need to take some additional computational resources, especially for a larger app. So you do need probably a fairly good machine if you want to build a larger native image application. So you need a powerful machine, but also native image doesn't do out-of-the-box cross-platform, cross-architecture compilation. So it needs to happen on the target architecture and operating system. So if I'm using my ARM Mac, out of the box, I will produce a native executable that is suitable for this architecture and this platform. But again, there are ways around it. So one thing you can use is GitHub Actions, and there you can build native executables for all the platform for which you would need to ship your application. And what is even better, so native image, again, needs a powerful machine, but also it might need some memory to make all those things happen, because there is a lot of work happening at build time. But we are working to reduce those memory requirements of native builds. So even in environments that are maybe less resources rich, it's possible to build even bigger application. So even if you have, let's say, 2 gigabytes of memory available, you can still build many even bigger applications with native image. So those memory requirements are going lower over time. And what we also recommend is that, again, native compilation can take time. So probably you don't want to do this native compilation every, I don't know, few seconds of minutes as you are developing your application, especially if the changes that you are making are mostly around the business logic. So we recommend to do this as a more or less final step before the final deployment, or once in a while, but in general, develop your application on a JVM and then compile to native closer to deployment. Don't do this every few minutes. And for the best peak throughput, one thing you could use is profile guide optimizations. So again, as we know, the way JVM optimizes your application at runtime is because it collects profile information of what is happening at runtime and which parts of your application are executed more often, and it adapts on the go. And it's very hard to beat that, especially if you are compiling something ahead of time under closed wall assumption and this runtime information is not available yet. So the way to work around it is to use profile guide optimizations, where you would run your application in the instrumented binary mode, and you would collect this profile information, and then you will feed those profiles to native image, so that it can build application that is kind of aware of the runtime behavior and which parts of your code will become hot. And this way, it's possible to achieve peak performance with native image that is on par with the JVM, as I showed you previously in demo. And I want to use this chance to talk a bit about what is new in GraalVM. So one thing is that we are trying to keep up with the latest Java releases, and as soon as there are new Java versions, we are trying to produce builds so you can use the latest Java features with the latest of GraalVM features. So at the moment, we have JDK 20 developer builds available, and on June 17th, we will have the actual production-grade feature release available as well. So at the moment, if you want to use JDK 20 builds, we have those available as developer builds on GitHub. And talking about new features, so one of the common requests that we are getting from our users is that as they are adopting native image specifically for production workloads, they are asking us about monitoring features. And for that, we added quite a few things in the last couple of releases. So one is, I think this was added in the previous release, we added support for JVM stat. So if you're using Visual VM, you will now also see native executables there as well, and you can observe things about them, such as, for example, memory usage, look at heap dumps, etc. And also, we are working with the community to enable GFR support. It's just that if you want to use any of those with native image, you would need to pass this one flag either on command line or in your build file to tell native image to build an executable that has those monitoring features included. But we are working to build this out, and we'll have some more releases in some new features in this new release in June. And if you want to see what else we are working on, as an open source project, we also have a community roadmap on GitHub. So there you can see what we are working on, what is coming up next, what is coming up a bit later in the year. And you can also share your feedback with us about which features you think should be implemented first, or what you think is missing in GraalVM. And one of the features that I'm very excited about the next release is that we are adding ZGC support. This is for now added on the JVM. So if you're using GraalVM on a JDK as a JDK, you can now use that GC as well. But we are also working on some new GC implementations and improvements to existing GCs in native image mode as well. And other things that we are working in native image are the following. So one, we are working with many framework and library teams to make sure that you can use more libraries in the native image mode as well, and making those libraries compatible with native image so that you can build your library, your application with whatever libraries you are using. Also, we are working with all those framework teams that I mentioned in the beginning to make sure that they have support for the latest native image features, and it's easy for you to build those applications using any of those frameworks. And we are also actively working to reduce memory, but also the time that it takes for the native image to build your application, so to improve this kind of feedback loop that you're getting when you're building your application with native image. And to get started with any of this, this is how you can get the latest release of GraalVM. So this will just curl you the download from our website, and the last release at the moment is 22.3, and it includes, for example, JDK 19 builds. Or if you're using SDK Man to manage your SDK installations, you can just install GraalVM with SDK Man as well. So to just repeat what you can accomplish with GraalVM, that's the following. You can make your application start much faster as native executables without JVM. You can reduce resources usage because we are not executing your code dynamically at runtime anymore. You can add additional security layer to your application by eliminating unused code and making reflection and serialization available through allow lists. And you can also achieve small container images if you want to deploy your applications and scale them faster. And tomorrow there will be actually one more session from Thomas that I hope will also mention GraalVM and how you can work specifically with Spring Boot applications and compile them as native executables with GraalVM. So if you're around tomorrow, make sure to check out Thomas's session as well. I think it will be in the same room as well. And with that, thank you.